We're going to continue our exploration of electrophilic aromatic substitution found in chapter 22. This would be chlorination, this first one. And sulfonation, this one. Sulfonation makes a sulfonic acid. I'm sure you remember a more common sulfonic acid called para-toluene sulfonic acid. I hope so. So yes, you would know how to make para-toluene sulfonic acid if instead you put a methyl group on here first. And sulfonation would make para-toluene sulfonic acid here and orthotoluene sulfonic acid here. Major and minor. Once again, why major, why minor? Well, one reason is there's a group up here. Putting a group adjacent to it has steric hindrance. Putting a group para to it, there's no steric hindrance of this first group for the second group here. And the ortho-para versus meta reason we'll talk about later. We haven't done a meta yet. So chlorination, how does that work? Well, you may have guessed FeCl3 is a catalyst, and it starts off a lot like the aluminum one. You take this really reactive electrophile, which is still not reactive enough to react with benzene, chlorine. You force it to be a nucleophile, which will make it a super electrophile when we're done. You don't see chlorine doing that every day. You gotta have something real special to make it do that. An electron-deprived iron in this case. And then this thing breaks off like this. Check this out. Oh, wow. Cl that lost a bond. That is a very unhappy Cl, a chlorine cation. It's the first time I think you've ever seen one. Pretty sure. That's a hopped up electrophile, and what's going to become the catalyst again very soon is the other piece. FeCl3 with an extra chloride on it. And I want to remind you, these guys are metal with an anion and four groups on it, many groups on it, called a complex ion. You might remember those from your 141 days. I think you guys can figure the mechanism out now. I had a nod back there. I like to see that. So pi, any pi, because benzene doesn't have a group on it, attacks. Right. Got a dead spot on the screen there. Sorry about that. Trying to get through it. There we go. We got a cation on carbon. We got a new chlorine. We have an old H on the same position. These double bonds never reacted. And I think we're going to get our catalyst back and make our product and make HCl at the same time. HCl, black H, blue Cl, be a black Cl. Cl takes its electrons, grabs the H, very fast re-aromatization step. And you've got your chlorinated benzene. And then sulfonation. I anticipate I'm going to do one of the reactions above and one below. Sorry about that again. And sulfonation. This is just sulfuric acid and heat. It's a little on the nasty side. It's called fuming sulfuric acid. Doesn't sound like you would want to be around, right? And when you heat up sulfuric acid like that, you force it to auto-dehydrate. Why? Auto-dehydrate? You take your sulfuric acid, which looks like this. And we're going to go red first, blue second. Because you got to make it lose water. And when you have to make things lose water that have hydroxyls on them, generally the first step is to protonate one of those hydroxyls. No difference here. So what's going to give a proton? Sulfuric acid. The green sulfuric acid is going to be the reactant. This sulfuric acid is going to be a catalyst. Protonate to make it a better leaving group. In so doing, you're generating a base. That can deprotonate the beta position. Sigma becomes pi. Water leaves. You got your H2O. And your super electrophile this time is this, SO3. SO3. Yeah, everything. I put it at the top too. So if I want to make the first product, I need to use this pair of pi electrons. If I want to generate the next one, I better use the ortho pi electrons. I'm copying chlorobenzene down here because I need another copy. Hello. Dangerous spot of the screen here. Same arrows as the top of the screen. Let's see what we get. And there and here. So up here, we're going to have no change, no change, no change, new group. Still has a double bond there. Still has another double bond. And has an O minus. Sulfonic acids are for these products. If it can get, it won't let me get my own label. So mean. There. And where's the H that has to go away? On the carbon with the group, the new group. Where's the cation? On the other carbon of the pi. That's now got an octet violation. What's going to take that H? Well, 2, 3, 4. You could say that O minus is going to grab the H. You could do this on a test and you'd lose a point. What? You'd have to acknowledge that that O minus cannot reach the H. It's too close. So you just write intermole right on that arrow there. And you're done. You could use the hydrogen sulfate from the catalyst too if you want. Then you'd have to use a sulfuric acid later to put an O minus into an OH. Yeah, this way it's the most economical is what I'm trying to say. And that's going to give the first product listed. And going down here, I don't want to lose the screen up there. So this one's going to be the ortho position. Didn't touch this, didn't touch this, didn't touch the chlorine. Got a cation there. Got an old H here. Got your SO3 O minus over here. Grabs the H, but it can't reach it. Got a right intermole. Right there. Intermole. Okay. And that, I think, is the whole deal, isn't it?